In this third part, we will discuss about belt friction. So suppose pulley and this is a belt passing through the pulley. So we will discuss what will be the frictional force that will act when this belt is about to slide. So suppose the tension here is T1 and tension here is T2, and these P1 and P2 are the points of tangential contact between the belt and pulley. So first thing we will do is to make the free body diagram of the element. So we will consider this element, and the free body diagram of this element has been drawn here. So as you can see, suppose here on the left side we are having a tension force of T, and suppose on the right side we are having a tension force T plus delta T, and this reaction force will be in the vertical direction delta n, and this frictional force will be from the law of static friction mu s delta n. Okay, so this is the free body diagram. Now from the free body diagram, summation of fx will be equal to 0. So in the x direction we have t plus delta t cos theta by 2. So this angle is theta by 2, and the component of this force will be here like this. Okay. Similarly, we have minus t cos theta by 2, and minus this is the frictional force which is also in the x direction. Similarly, you can write for y delta n. This is the force, and we will have two components. One is this, and another is here. So our equation becomes this. Okay. Now what we can do, we can solve for delta n from equation this, and we can put in the second equation. Then finally you will obtain this equation, and when you further divide by delta t, then this is your final equation. So delta t by delta theta cos delta theta by 2 minus mu s t plus del t by 2 into sine del theta by 2 divided by del theta by 2. Okay. Now when suppose if delta theta is very small, then this term becomes 1 because cos 0 is 1. So when delta theta approaches 0, this term becomes d t by d theta, and also you can also neglect delta t because as delta theta approaches 0, so this delta t will also be negligible. So this will be 0, and for small values this sine del theta by 2 will be approximately equal to del theta by 2, and which will cancel out. So finally we get this equation dt by d theta minus mu s t. So this is a differential equation. You can easily solve this by using the variable separable method, and you can integrate it from theta is equal to 0, theta is equal to beta. Because your angle is changing, maximum angle is this beta, and minimum possible angle is 0. So when you solve this equation, the solution will be ln t2 by t1 is equal to mu s beta, and you can also write t2 by t1 is equal to e mu s beta. So this is the solution of this equation, and this is equation governs the belt friction. Okay. One problem related to belt. So as you can see, a flat belt connects pulley A to pulley B. So this is the pulley A and this is the pulley B, and this belt connects both the pulleys The coefficient of friction are mu s is equal to 0.25, static friction and kinetic friction is 0.20 between both pulleys, knowing that the maximum allowable tension is 600 pound. So maximum allowable tension is this. Determine the largest torque which can be exerted by the belt on pulley. So this is our problem. Now how we are going to solve this? So this is the strategy. The key to solving this problem is to identify the pulley where slippage would first occur. First, by our knowledge, we should identify on which pulley slippage can occur, and then find the corresponding belt tensions when the slippage is impending, as we have done in the previous equation. The resistance to slippage depends upon the angle of contact beta as well as upon the coefficient of static frictions. Now this mu is same for both the pulleys. Slippage occurs first on pulley B, for which beta is smaller. So the chances of slippage will be more on smaller pulley. So now let us solve this problem. Body diagram on the first pulley as we done during the derivation. So this is T1. T2 is given maximum 600 pound, and this is the solution which we have already obtained. T2 by T1 is equal to E mu s beta. So from this we can obtain T1 as 355.4 pound. Now let us make the balance on bigger pulley. So this is the free body diagram of the big pulley. So by summing the moments about A, we have MA, and we will have the moments because of these two tension forces, T1 and T2, and this 8-inch is the diameter of the pulley. So MA plus 8, and this is the resultant of these tension forces. So finally the moment comes out to be 163.1 pound foot. Now from the solution we can check that the belt does not slip on pulley A. Can also check it by computing the value of mu s required to prevent the slipping at A, and then verifying it with the value of mu s. Okay, so now applying this equation for second pulley, mu s beta and this. So this comes out to be 0.524 mu s beta. Now this beta for bigger pulley is 240 degree, which is 4 pi by 3 newtons. So from this we can calculate mu s, and mu s comes out to be 0.125, which is much smaller than the frictional force, maximum friction, 0.25. So we can say that the slippage would not occur on the pulley A. So this is all for this. Thanks for watching.